Okay, so I'm talking about Avogadro's hypothesis and stuff on there. Avogadro's hypothesis that we could tell equal volumes of gases had equal numbers of particles, and evidence for that kind of stems from the testing we did between hydrogen and oxygen and water and the volumes and how they combine was really what they used for some of the evidence. But I mean, this is all about matter. That's what we're talking about in Unit 5. Matter. You see that? Okay, so we're talking about particles, and we should know, of course, that particles would be atoms, would be molecules. Okay? So we want to write all these down. I'm going to have you guys turn this in as notes for a grade tomorrow. Everybody make sure you're writing this down. So some different classifications of matter. So first topic, we'll talk about these things called elements. Should definitely know what elements are. There's a whole periodic table filled with them that you guys have. So I can tell elements, first of all, by capital letters, right? So if I saw something like this, I know that that's a symbol for an element because there's just one capital letter. Or maybe something like this, or maybe something like this. Just one capital letter. What this means is that an element consists of only one type of atom. Okay, it's important to note that it's not just one atom, one type of atom. So there are a huge number of atoms, but they're all the same type within an element. Okay, it's a pure thing. It's just all one type of atom. Okay, we can combine them though, and when we stick them together, we make molecules, or what we talk about as compounds. Okay, so compounds are when we have more than one type of atom. And they're stuck together, which we say chemically combined. They're stuck together by these things called chemical bonds. So the beginning of this unit, I don't know if you guys remember it or not, but I know we build up through the unit and it gets harder with some of this math and stuff, but realistically, the beginning of the unit was pretty easy. So there's going to be some questions on there that are really going to help you out, just paying attention and know them. Okay, so this is when we see things like H2O. So all together, I see stuck together. There's no space in between. There's no and in between. Nothing like that. It's hydrogen, two of them actually, stuck together with oxygen. Or maybe carbon stuck together with oxygen, like CO2. All right? Or maybe we have carbon monoxide. Okay? Carbon monoxide, would it be like that or would it be like this? The first one, it's a compound. It's more than one type of element. What does the second one look like to you? That's just one element, right? How can you tell? One capital letter, right? So this is some different element called cobalt, actually. So that's not a compound. All right, you got to pay attention to that. Sometimes that gets people. you stick two letters together and one's capitalized and one's lowercase, or what happens more often is when you have two capital letters stuck together and then people think it's just one element and they're looking all over for it. All right? Okay, so compounds. Piece of cake. So in compounds, we can write chemical formulas. So if I wrote H2O, I should be able to ask you how many atoms are in H2O. What would you say for that? How many atoms are there? Two hydrogens and one oxygen, which makes three atoms. Okay, it's pretty easy. It's not too tough. Carbon dioxide would also have three because it's got one carbon and two oxygens. This would only have two because it's just one carbon and one oxygen. So that's pretty simple, right? What's a little more difficult, okay, is if you had something maybe like this. Where we have parentheses, okay? So I could ask you some questions about this. I could ask you, first of all, how many different types of elements are there in this compound? What are they? There's Ca, right? There's N, and then there's O. All right, so I should be able to ask you how many, or I should be able to ask you what elements are in the compound. I should be able to ask you how many different types of elements are in the compound, 3. I should be able to ask you how many atoms of each are in the compound. Okay, so anything outside the parentheses, easy, just our normal rules. Ca is outside the parentheses. So we just look at its subscript, which it doesn't have one. So if it doesn't have one, how many are there? Just one. Now if it's in parentheses, it's a little different. We look at its subscript, and we got to multiply that subscript by what's outside. So n in parentheses does not have a subscript, which means that I'm going to take what's inside and I'm going to multiply by what's outside. So 1 inside, multiply by 2, and that's going to make 2. Okay? Oxygen, we have 3 on the inside, multiply by 2, there are 6. So how many total atoms do I have in this one? 9. Add them all up. Okay? Pretty cool with that. Noise. What's up? Oh. All right, so that's kind of our elements and compound stuff. And then we started talking about this unit that we call the mole. All right? So 1 mole of any substance is a certain number of particles. Okay? 1 mole of any substance, doesn't matter what it is this number here, 6.02 times 10 to the 23rd. And it's particles. And so the reason why we write particles instead of atoms or molecules, because those are particles, is because it depends on the substance you're dealing with. If I'm just dealing with an atom, just a symbol like, say, silver, 1 capital letter, so that's just an element, then I'm talking about 6.02 times 10 to the 23rd atoms. Okay? But if I had a compound that's more than one element stuck together, so in this case H and O, then it's going to be molecules, which you guys know. I probably shouldn't do it this way, but I abbreviate it MCS. Okay? So 1 mole is that number of particles. It's a huge number. Okay? What we learned about after the mole, after we did some work with this, and talking about this, we have a conversion factor. We can say if we just compare our amounts. It's kind of like we do our for every statements. So for every 1 mole, there are 6.02 times 10 to the 23rd particles. Okay? which I can also show like this. 1 mole per 6.02 times 10 to the 23rd particles, representative particles, RPs, atoms, molecules, that's what that stands for, depending on the substance, right? And I can also say it the other way. For every 6.02 times 10 to the 23rd representative particles, there are 1 moles. That doesn't sound right grammatically, but nevertheless, it does show the for every statement. And we use that as a conversion factor in our math problems that we do, right? So we actually use this conversion factor whenever we're dealing with any problems that deal with particles. So whether I'm starting with atoms or molecules and going somewhere else, or if I'm starting somewhere else like moles and going to particles, whatever particles is involved, I'm going to use one of those two things based on how I'm trying to cancel the units. Okay, we also talked about how we can find the mass of 1 mole. We talked about relative mass a little bit. We made our lightest element. We said this is going to be 1 gram is considered to be a mole of hydrogen. Okay? And so then we can say that oxygen is 16 times that, so it's going to be 16. So we developed these things called atomic mass units to represent masses of atoms. And then we can change out atomic mass units with grams, something that we can actually observe and use, to talk about the mass of 1 mole of a substance. And what we call this is we call it molar mass. Cool. It's not the same for all elements. Not all elements are same. We get this value by looking up the mass on the periodic table. So this tells us the number of grams in 1 mole of a substance. Okay, so that's molar mass. And all I got to do to find the molar mass of an element, say like sodium, Na, what's the molar mass of sodium? Just look at the periodic table. I look up Na, and it says it's 22.99. But pay attention to those units, what it really means. You have to understand what it really means. That's the number of grams in 1 mole of sodium. So you can put it as grams per mole, or you could write it as 22.99 grams per 1 mole, which is actually a little more writing, but it's a better way to write it because that's how we use it as a conversion factor. Okay, we use molar mass as a conversion factor just like we used Avogadro's number, right? We think of these conversion factors like tools to solve our problems. So I write some kind of mass per 1 mole. Mass from the periodic table, some number of grams from the periodic table. Or depending on how I need the units to work, that would be grams on top. I might have the mass in grams I might need to put on the bottom. So I put grams on the bottom when grams is the unit I'm trying to cancel out. And I'll talk about how we set up those problems just in terms of looking at our conversion factors in just a second. But so elements, really easy. Just look at their mass in the periodic table. Sometimes we have other things though. Sometimes we have compounds. All right. Sometimes we have something like, um, well, we do H2O. Let's use H2O. We've done that several times. So if it's H2O, just like we did the element, but I got to do each individual atom. So H2O has two H's and one O, and we just look up the individual masses. Hydrogen on the periodic table is 1.01 grams, and then oxygen is 16 grams. And if I add them up, I get 18.02 grams. So there are 18.02 grams per mole for water. That's water's molar mass. You just add up everything that's in the compound. That gives you molar mass. So still, I think you guys are pretty confident with this as far as I can tell from what I've seen, quiz-wise and otherwise. Most of you guys can do all of this stuff. But what really gets us is when we get into the different types of problems like converting from mass to moles or moles to mass, or really difficult that a lot of people struggled on the last quiz, which is taking a mass and going all the way to the number of particles, or taking a certain number of particles and going all the way to mass. So this next part, really pay attention. I know I'm making a video, but feel free to raise your hand and stop me, and I'll just pause it and answer any questions you might have. These conversion factors, by the way, you're not necessarily given Avogadro's number on the test. Like, you kind of need to know it. But in doing questions, you're going to see Avogadro's number, so that stuff will be there. Those conversion factors will be there. There's half of the test, or actually 3/4 of the test, is going to be multiple choice, and then part of the test is going to be short answer. Okay? So, using the conversion factors. All right, so we're going to start with the most common one to actually do, which is a mass to mole problem. So in a mass to mole problem, what this means is I'm going to start with mass, and I'm going to ask you to find the mole. The mole is like the central unit. This is just one step. And whenever we have mass involved, that means that we are going to use the molar mass as our conversion factor. Okay? That's our tool for this type of problem. So what I would say in this is I'm going to tell you, you have 15 grams, just make it up a number. You have 15 grams of carbon, and I want you to tell me how many moles that would be. What conversion factor would you use? What would it look like? So we already established that the conversion factor has to be molar mass because we're dealing with mass. Whenever you're dealing with mass, going from mass or to mass, you got to use molar mass conversion factor. But now the question becomes, what am I going to use next? And so all you got to do is look at the unit you have here and know that it's got to go on the bottom. So if I do molar mass with grams on the bottom, that means instead of doing grams per mole, I'm going to do mole per grams, which means 1 mole over some number of grams from the periodic table. Okay? Which if I looked at the periodic table for carbon, I would see that it's 12.01. Okay? So for every 1 mole of carbon, there are 12.01 grams of carbon. Does that make sense? And so what you're doing is in any of these problems, you're starting at one spot, you're trying to get to another spot. In this problem, we're starting with the mass, and we're trying to get to the units to moles, all right? So when you use a conversion factor, what that does is that you put on the bottom whatever unit you already have so that you can cancel it, and on top, you put where you're going to. So this is what you have on the bottom. And on top, what you are going to. Emphasis, exclamation point. And that would solve the problem. I'm not going to go ahead and worry about the calculation. Be about 1 1/4, 1.25, something like that. But now if we were going to go the other way, which I would call a mole to mass problem, again, just ask yourself, you've got two conversion factors. Are particles involved, or is mass involved, or are they both involved? Particles aren't mentioned anywhere here. Okay, mole, that's a unit all itself. All right, so particles aren't mentioned. Mass is, though. So if I see mass anywhere in this type of problem, I'm going to use molar mass. So for this type of problem, what I would do is I would say you have 2.5 moles of zinc. How many moles would that be? I'm sorry, how many grams would that be? And I could switch around and say, how many grams would 2.5 moles of zinc be? Whatever, it doesn't matter. I'm giving you the number of moles of zinc. So what I tell you to start with, that starts the problem. So since mass is involved here, I know I'm using molar mass. I also know that I have the units mole. So again, where do I put the units that I already have? On the bottom. So I'm going to put mole down here. So if I use molar mass with mole on the bottom, I'm going to have some number of grams on top for zinc. And on the bottom, I'm just going to have the 1 mole. Okay? And if I want to know how many grams of zinc are in 1 mole, I just look at the periodic table. And I look up Zn, and it says 65.39 grams per mole. There are 63.59 grams for every 1 mole of zinc. So the units that we initially had, they're going to cancel out. And the units we're going to end with are grams, which is mass, right? Problem solved. I could just multiply across the top, get an answer. The bottom's just going to be 1, so we could pretty much ignore that. So whatever 2.5 times 63.59 is, that answer goes here, and we're done. Up here on the top, same thing, just multiply across the top. I'd end up with 15 moles of carbon. Divide it by 12.01, and whatever that answer comes out to be, there's my answer. This also helps you. I know some of you, now you really got to be able to show your work and do this with the units in the problem, canceling them out this way. But it also shows you, like if I do a problem mass to mole, I'm seeing that this is on top and this is on bottom. Really what that's telling me is, all right, I'm going to take the 15, I'm going to divide by the molar mass. So that's how I do mass to mole. If I'm doing mole to mass, I'm going to take the moles and I'm going to multiply by the molar mass. Okay? There's some talk too if you're doing these types of problems, just kind of logical reasoning, just thinking. So in the other classes, they talked about scaling up and scaling down. Since I'm using the same test as them, you're going to see this scaling up or scaling down. But like, if I told you that the mass of zinc is 63.59, and we have 2.5 moles, would you think that we would scale up or scale down? Scale up. Right. What does that mean? Why would we say that? So if we know that 63.59 grams is the mass of 1 mole, but we don't have 1 mole, we have 2.5, we know we're going to scale up. By a factor of what? 2.5. Okay? What if the molar mass is 12.01 grams and we have 15 grams? Would you expect the number of moles to be greater or less than 1? Greater. Okay? And if we did this, solve this at the end, like I said, it'd be about 1.25. It would be greater than 1. Okay? Rachel? So you guys have any questions on that at all? Does that make sense? Now let's talk about problems that don't involve mass, that instead involve atoms or molecules. Okay? So I would call this a particles to mole problem. Okay? So in this scenario, we start with particles and we're going to moles. So whatever we start with, it's going to be the same deal. Now here, though, what we say is we ask, are particles involved or is mass involved or both? In this case, mass isn't mentioned anywhere, particles are. So in this scenario, the conversion factor we're going to use is going to be 6.02 times 10 to the 23rd, whatever units we have here, atoms per mole. That's what we're going to use, but not necessarily that way. We might have to flip it upside down. Same thing I just told you on the last part. Whatever unit you're starting with, that same unit goes on the bottom, right? The unit you already have goes on the bottom. So that tells me I'm going to flip this upside down. So the 6.02 is going to go on the bottom, and the 1 mole is going to go on top. And if I check how my units interact throughout this problem, the atoms cancel because there's one on top and one on bottom. I'm left with moles, and that's what I'm trying to find. So good. That works. So I would use mole on top, Avogadro's number on the bottom. So it looks like if I had a particles to mole problem, I would take the number of particles and divide by molar or by the Avogadro's number. Multiply across the top, 2.4 times 10 to the 24th. Multiply across the bottom, 6.02 times 10 to the 23rd. Now, this did cause some problems when we dealt with the scientific notation, people understanding how to multiply and divide scientific notation, which all you got to do is think of the front part as just normal numbers and just do whatever you need to do with them normally. So I would just divide there. So 2.4 divided by 6.02, and that would come out to be like 0.4. All right? And then what you do is you write times 10, and then you take the top exponent and subtract the bottom one. So your answer would be 0.4 times 10 to the first moles. Which really, 10 to the first is 10. So really it's 0.4 times 10. So really it's just 4 moles. Now, if I went the other way and did a moles to particles problem, same idea. We're going to use the same conversion factor because the only thing that's involved in this problem is particles. I'm starting with moles, so that means in this case I would tell you something like you have 4 moles of something. All right, so we have 4 moles. We know that we are going to use Avogadro's number because it's just a particles problem. Okay, and we know that the mole part is going to go on the bottom, so that means Avogadro's number must go on top. Let's say atoms. Let's pretend I'm talking about some element, lithium, Li. Okay. So in this case, all we do is multiply. However many moles we have, just multiply by Avogadro's number. We know that there's Avogadro's number of particles in 1 mole, so if I had 4 moles, it's just 4 times that, right? Doesn't that make sense? And then same thing that we did before, just take your, this only has a normal number, there's no times 10 part to it. Multiply by that by the normal part of the scientific notation, you get 24.08, but you can't leave the times 10 to the 23rd off. So I'd write times 10 to the 23rd atoms. Could see that on multiple choice as possibly 2.408 times 10 to the 24th, which is the same value. I just moved this decimal 1 to the left to make it a number between 1 and 10. Going from 24 to 2 is going to make it smaller. I have to compensate by making the exponent 1 greater. Okay. So you guys did, on the quiz, you did okay. So some people are doing really well on that. Some people are still coming along on that. The one that got everybody was when we did things like mass to particles or grams to particles. Okay? And you guys got to understand that mass and grams just interchangeable, same thing. Okay? Whenever you see mass, it's grams. If you see grams, you're talking about mass. So this is what got people. We're doing a mass to particles. So I say something like you have 40 grams of oxygen. How many atoms would that be? So you just write down what you're starting with. Put it over 1. All right, so which conversion factor do we use in this problem? Are particles involved? Particles are involved. We're trying to find particles. So that means we're going to have to use Avogadro's number. Is mass involved? Mass is also involved. So this is one of those where both of the conversion factors are involved. It's what we call sometimes a two-step problem. It's like you got to figure out one thing first, and then you can figure out the real answer. So this is how we do it. What are we starting with? Mass, right? So we're going to use molar mass first. Use that conversion factor first. And I know that grams have to go down here. So I'm doing first the molar mass of oxygen. How many grams are in 1 mole of oxygen? Anybody know off the top of their head? 16. So 16 grams, I know it's 16.00 on your periodic table, of oxygen per 1 mole. So what this tells me is grams cancel out, and if I solve right now, I'll find out how many moles of oxygen 40 grams would be. And I'll do it. So multiply across the top, which is going to be 40. Multiply across the bottom at 16. It's really 40 divided by 16, right? So if I do 40 divided by 16, I get 2.5. All right, so I know I have 2.5 moles. Almost don't be done in another 11 minutes. So now I've taken care of the mass part of the problem. Now I'm on the particles part of the problem. So now I'm going to use Avogadro's number, and I know that mole has to go on the bottom. So I got to put Avogadro's number on top. And again, I just do 2.5 times 6.02, which is going to be about 15. About 15, right? Right, times 10 to the 23rd atoms, or 1.5 times 10 to the 24th. So in those situations where mass and particles are both involved, we got to use both conversion factors. Make sure you're writing all these, because when I check those notes for points, I'm going to make it worth a lot. I'm going to grade them based on what's included. So those are the math problems. I'm not going to worry about doing a particles to mass. It's the same idea. It's just that if particles is first, if that's what you're starting with, then use the Avogadro's number conversion factor first, and then use the molar mass second. Okay? So use the conversion factor that applies to what you're starting with first. Use a conversion factor that applies to what you're trying to find second. That's all there is to it. The next thing we talked about was percent composition. So when you get a percent composition problem, you're going to get a compound. What's the percent composition of H2O? Okay? Which means, first of all, find out the different elements that are in the compound. What's in H2O? There's H and there's O. All right? I want to find out what percentage of that compound is hydrogen and what percentage of that compound is oxygen. So what we're going to do is we're going to do our molar mass. Okay? We're going to find the molar mass of this. So hydrogen, there's 2 of them. Oxygen, there's 1 of them. Look up their masses on the periodic table. Hydrogen's 1.01 and oxygen is 16. Okay? So the total hydrogen is actually going to be 2.02. Total oxygen is 16. So the molar mass of water is 18.02. So 18.02 is what we're going to use as the total amount, okay? So the whole thing, the whole H2O is 18.02. When I want to find the percent hydrogen, I want to know just what part of that 18.02 is hydrogen. So we look at the part that's hydrogen, which would be the 2.02, and you take the part and you divide by the whole thing. All right? So 2.02 comes out to be a decimal 0.112. Now, this is not the percentage, this is the value. To make it a percentage, you multiply by 100%, which means just move the decimal 2 to the right. So the hydrogen makes up 11.2%. And now, since this compound only has hydrogen and oxygen in it, I know that the oxygen would be 88.8%. Why? Because if that's everything that's in the compound, it has to add up to 100%. But we can still check it. This is a good way to check your work. So 16 of the 18.02 is oxygen. If I take 16 and divide by 18.02, I get 0.888, which again, when we change that value to a percentage, 88.8%. Cool. All right. So that's how you do percent composition. The last thing we have to do is empirical formulas. In empirical formulas is just the simplest ratio of elements in a compound. So one really common compound to life is this one, glucose, C6H12O6. Okay? That's the actual molecular formula of glucose. Glucose actually has 6 carbons and 12 hydrogens and 6 oxygens. That's called the molecular formula, what's actually in it. Empirical is the simplest ratio. So can I break that ratio of 6 to 12 to 6 down into something simpler? All those are divisible by 2. They're all divisible by 3. Heck, they're all divisible by 6. Nothing greater than that, though, because my lowest subscript is 6. So if I divide them all by 6, the empirical formula of that would be C, just 1, because 6 divided by 6 is 1. H, 2, because 12 divided by 6 is 2. And then O, just 1 because 6 divided by 6 is 1. That's empirical formula, simplest ratio. But being the nice guy that I am, I did, of course, do one where I had percentages. Okay? So let's do. Dang, I was gonna do the one from your last quiz, but that's pretty intense. I didn't put one of these on your review, did I? All right. So on your last quiz, you had this thing, and I'm gonna give you this saying that Miss Bauer taught me that helps, and you might want to write it down and memorize it. Could be helpful. So on your last quiz, I told you there was 57.14%. This is NutraSweet. 57.14% carbon. There was 6.16% hydrogen. There is 9.52% nitrogen. And there is 27.18% oxygen. Okay? So the first thing you do is change the percentages to grams. Okay? We're pretending that there's 100%, so we're going to change that to grams. So that's the first part of the saying they have, percent to grams. The second part of the little poem goes grams to moles. Okay? Percent to grams, grams to moles. So the 57.14 grams I want to find out how many moles of carbon that would be. So it's just a mass to moles problem. It basically means that I'm just going to divide by the molar mass, which for carbon is 12.01 grams. That means that carbon is going to come out to be 4.76 moles. Okay, if I do the same thing for hydrogen, 6.016 grams, divide by its molar mass, then I'm going to find out that hydrogen has 6.10 moles. Nitrogen, if I take the 9.52 grams, divide by its molar mass of 14.01, I'm going to find that that is 0.68 moles. Oxygen is 27.18 divided by 16, its molar mass, right? And that comes out to be 1.7 moles. Okay, so percent to grams, grams to moles. The next thing is divide by small. So out of all these numbers of moles, divide by the smallest one, which is going to be the 0.68. And what I'm hoping works here is I'm hoping these all divide out into whole numbers because that's what we got to get. But when we do that, we're going to find out that the carbon comes out to be 7, and the hydrogen comes out to be 9. The nitrogen, of course, 0.68 divided by 0.68 is going to be 1. The O, 1.7 divided by 0.68 is, oh man, we were doing so well too, 2.5. So, percent to grams, grams to moles, divide by small, now multiply till whole. So let's multiply all these by 2 and see what happens. O times 2, 2.5 times 2 would be 5. There is your molecular formula. I'm sorry, empirical formula, not molecular. Going to the molecular formula is the next step. Now, I know, and right after this. So if you have to then go to the molecular formula, you need to know the molar mass. And so if I told you the actual molecular formula is molar mass, or the molar mass of this compound is 294.3 grams per mole, what I'm expecting looking at this is I'm expecting this will be maybe 1 time greater, or 2 times, or 3 times greater, or 4 times greater mass than the empirical formula. And if it was 2 times bigger, I would just double all these. But what I find is when I add all these up, the mass of this is about 294.30 grams per mole, which means I'm going to just keep it the same. It's a 1 times, so this is the molecular formula. The molecular formula can be the same as the empirical formula.